Hello everyone, this is a short video on programming language translators and how to solve questions of parsing tables. First of all, I would like to kindly acknowledge my faculty, Professor Kanna Rasana, for giving me such an amazing opportunity to work on this, and VIT University for giving me a chance. So, next. So in this video we'll be learning on how to construct LL1, LR0, SLR1, CLR1 and LALR1 parsing tables using some examples. And at the end of the video we'll be discussing on activation trees and principle of sources for optimization. So let us consider our first example. Uh, Let us consider the given grammar as capital S gives capital C and another production as capital C gives small c capital C slash d. Okay, so in order to solve this question for LL1 parser table, we need to check that our given grammar is not left recursive grammar. So if we have any production of the form capital X gives capital X alpha where alpha is a non-terminal or a terminal string, then our grammar is left recursive. But fortunately here we don't have any such kind of production, so our grammar is not left recursive. Moving on, we need to also check that our grammar is not left factoring. That's how, if we have a production like x gives a alpha 1 or a alpha 2, then our grammar is left factoring. Here also we don't have any such kind of production like that, so our grammar is non left factoring. Now we need to calculate first and follow for the given grammar. So the first to compute first for any string x, the given algorithm is this. If you need to follow the algorithm, just read through this, and for follow is this one. Okay. Now for our given grammar, we'll calculate the first and follow. For the first production, capital S gives capital C. If we apply the first rule over this, we'll get first of S is equal to first of C. Also on the second production rule, if we apply first rule, then we get first of C is equal to character C and character D. Thus how the first of S will also be capital C, capital D. Now finding follow. According to the first rule of follow, if the S is the starting symbol, then dollar is in follow of S. That's how we got follow of S is equal to dollar using rule 1. Now if we use the production S gives capital C, then the production then for the production uh, S gives capital C, we get follow of C is equal to follow of S, which is also dollar from this which we got. Thus follow of C is equal to capital C comma capital D using rule 3. Thus follow of S is equal to dollar and follow of C is equal to dollar CD. Moving on. Now will be calculating parsing table, LL1 parsing table for a given grammar. Thus the algorithm for that is this one. Now moving on directly to the table. Yeah. So we have all the non-terminals on the left hand side column and all the terminals on the top and the dollar sign. Okay. So for calculating the first of capital C, first of capital C is letter C and D. Now according to the given algorithm, for each terminal A in first of alpha, where alpha is C, that's why first of C is C and D. We add A gives alpha to M of A. Thus we added S gives capital C to C and S gives capital C to D in the row where the non-terminal is capital S. Moving on, for the next production, the first of C letter terminal C is C only. That's why we added letter C gives CC production to the first column and gives C gives D to the second column. Now let's calculate the SLR1 table for this one. So the step one is we need to construct the augmented grammar. For constructing the augmented grammar, we assume a grammar S dash gives S and all the productions of the S written separately. Thus, our grammar will be capital S dash gives capital S gives CC, C gives C, and capital C gives small d. Now we need to find the closure of our given grammar. So for finding the closure operation, the algorithm for this is this one, where initially every LR0 atom is added to the closure of I. Moving on. So we need to write the canonical LR0 collection for our given grammar. For writing the canonical LR0 collection, we write the closure of I at I0. Thus, the I0 will be S dash gives dot S. Now, for the first production, we see that after the dot, we have capital S. So we include all S productions into our I0 closure, because according to the algorithm, if A gives alpha dot B beta, then B gives dot gamma will be in the closure of I. Thus, we added S gives dot C into a closure of I. Now, after the dot, we have capital C. Thus, we added capital C gives dot C and capital C gives dot D. That's how we constructed I0. Okay. Now we need to use the goto operation and construct all the states. So applying capital S transition to I0 state. For capital S transition, after the dot we have S in the first production. So it will give us S dash gives S dot dot. The dot will jump after the S, after the goto operation. Thus we got our new state as I1 S dash gives S dot. That's how for all the non-terminals and terminals we construct the goto operation, and we get the following I0 to In states. Now we'll construct the SLR parsing table. For constructing the SLR parsing table, we use the following algorithm, where the most important part is the second point. Just try to recall this once we go to the table. Now the SLR table is this one, where we write all the states into the left hand side column and all the terminals and non-terminals in a sequential way on the top hand side column, top hand side row. Now consider the situation where we move from I0 to I3 using the transition from terminal C. Since the transition is using the terminal letter C and I0 is shifted to state I3, thus we write S3 in row I0 column terminal C. We go to the table and we see that we written I0 for the I0th row S3 in capital C, the small c, which is the terminal letter. Again we see that we also written S4 in terminal D. Let's see that the transition should be to I4. Yes, we can see that from I0 to I4 transition we use terminal D letter. Thus we can see that it's a shift operation, which is seen in the table as if a terminal, if A is a terminal where the production is A gives alpha dot A beta in II and go to operation is I of I comma A is equal to I of J, then action I of A is shift J, where shift is S3. Moving on, we write except for this one. Yeah. If S dash gives S dot is in I of I, then action I of dollar is except. So we have I of 1 having the production S dash gives S dot. So thus we write for I1 of dollar except. I1 of dollar except. Moving on, we write reduce operation for the following case. If A of alpha gives is in I of I, then action I of A is in reduce A alpha for all in follow of A, where A is not equal to S dash. Okay. we go to the table and we see where do we have all the productions and dot after that. Let's consider the case uh, I4 case. Okay, so in this state we have the productions capital C gives D dot. Here we see that it's a production from the initial state where the dot is after the terminal. So this is one production from the I0 state. Okay, so here for this I4 we write reduce operation because we have a final production in this state. Okay, so we go to the I4 row and we write, since it is a third production, we read R3 in all follow of capital C. Capital C follow is small d, capital small c, capital D and dollar. So we go to the table and we see that for I4 we write R3 in small d and dollar D. Okay, thus the SLR table is constructed. Now, since the SLR table has no multiple entries, the grammar is SLR1, hence proved. Moving on, constructing the SLR1 passing table. For constructing the SLR1 passing table, we construct the augmented grammar first, as constructed in the previous example. Okay. Now next we compute the first and follow. For constructing the first and follow, we use the same thing which we used in the past for the previous for constructing the CLR1. Okay, so we use the same values over here. First of s is equal to small c small d. First of c is equal to small c small d. Again, follow of s is equal to dollar. Follow of c is equal to dollar small d small c. Again, now to construct the canonical collection of LR1 zero items, the closure of I operation is given over here. Do look at it. Do have a look at it. Next, we construct the closure function and the canonical construction of LR1 items. So here, the difference from the CLR1 construction is the only thing is that after each production, we write the look ahead, which can be seen as the production carrying after the comma. Okay, so for constructing the LR0 closure of I, every LR1 item is in closure of I, and if A gives alpha dot B comma A is in closure of I, then we include B gives dot gamma comma B will be in closure of I for each terminal B in first of beta I, where beta A is this one. Okay, so moving on, we construct the closure function. Yes, for the first operation, $s gives dot s. Now for this production, the look ahead is dollar because we don't have any terminal after s. That's why the look ahead is dollar. Okay, now since after the dot we have letter s, thus we include all the productions from s into the state. Okay, thus s gives dot cc comma dollar. Now for this production, the look ahead is dollar again because for after the c capital we don't have any terminal letter in this. Okay, that's why the look ahead is dollar. Again we have after the dot capital C letter, so we need to include all the production starting from capital C. Thus we included capital C gives dot cc and capital C gives dot d. Now finding the look ahead of this, for look ahead we need to find the first of C is C slash D, so we write C comma D in the look ahead, and over here also we write C comma D because the same capital C letter is missing. Okay, moving on, we construct all the transactions involving the next letters. So here we have capital S, capital C, small d. So transitions are capital S, capital C, capital c, small d. Unlike like as we did in CLR1 construction, SLR1 construction, we do the same transactions over here also. Just we need to take care of the look ahead. So we add look ahead every time when we do the go to operation, as it has been seen in the previous state. Okay. So after constructing the closure operations, finally we move on constructing the LR1 passing table for this one. This table will be called as CLR1 passing table. So the algorithm for this would be as follows, where the second point is the main point for writing the values in the table. Now again, we go to the parsing table and we see that for I0th row, we can see that S3 and S4 are in column where the terminals are small c and small d respectively. So we go to the table and we see that there is an operation shift from I0 to I3 using small c. Okay, thus it is a shift 3 operation. So we write S3 for I0th row and terminal C column, as we can see in the table. Similarly, for D, the letter, we write S4 because the transition is to I4 state. Okay, so we go to the table for the D terminal in the I0th row, we write S4. Okay, now coming to the algorithm, we see that for the second point, if S dash gives S dot comma dollar is in I of I, then action I of dollar is in except. Coming to the collection, we see that for the I1 state, we have S dash gives S dot dollar. So we go to the table, we write for the I1 state in the dollar column, we write except, so that our strings get accepted. Now again for the reduced state, what do we see is if A of A gives alpha dot, comma A is in I of I, then action I of A, comma is in reduce A of alpha where A is not equal to S dash. According to this algorithm, if we come to the collection diagram, we see that for every state containing the production tool and a dot after that, let's see for an example, let's say I5 state. For I5 state, we have the second production, the production over here having the dot at the end. Okay, so it's the first production from our canonical grammar. Thus, we can see that it's the final state. We can't move after this. We can't have go to operation on this state. This is the final production. Okay, so since it's our first grammar, we go to the I5 state. We write R1 because it's the first production. We write reduce 1 for every terminal and dollar. Okay, so we go to the table and we write R1 for dollar. Okay, coming back again, because for we wrote only for dollar because after the comma we had dollar only. That's why we wrote in the table R1 for dollar column only, not for C and D. Let's see another example. Coming to the state I4, we see in the I4 state that it's also a final production. We can't proceed after this. So for this production, this is the third production rule. So we write R3 and I4 column, I4th row for C and D column. Let's go to the table and see. We have for I4th row for C and D we write R3 because it was the third production. So we write R3. Similarly, the constructing the table for the whole diagram as it is, we get that we get the LALR1 passing table. Now in the table we can see that there are no multiple entries, that the grammar is LALR1 passing table grammar. Constructing the LALR1 passing table for the same grammar, we construct the augmented grammar as we did in the past two examples. S dash gives capital S gives capital C, capital C, capital C gives small c, capital C gives D. We use the first and follow values as we used in the past. Okay, now constructing the canonical LR1 production rule for collection for LR LALR1 parsing table. So the basic difference over that side over CLR 1 and LLR 1 is that we combine all the productions with the same code into one state. Coming to the CLR 1 canonical collection, we see that for I3 and I6 state, yes, see that we have the same core. What is core actually? Core is this part after the production. C gives dot C gives C dot C. C gives C dot C. C gives dot CC. C gives dot CC. So we have the same core after this, but we don't have the same look ahead. In IC state we have look ahead as C and D, whereas in I6 state we have dollar. So in LALR table, while constructing the collection, what we do is we combine the states with the same look ahead into one. So moving on to the LALR1 closure, we combine I3 and I6 state over into one state, single state. Similarly doing it for other states also, as we get three new states. I3 I3 and I6 has been converted to I36. I4 and I7 has been merged into I47, and I8 and I9 has been merged into I89. Thus, what we get is the following table. Now constructing the LALR1 parsing table. For LALR1 parsing table, what we do is we use the same algorithm as we did over here. So writing the shifts, reduce and accept values according to the this algorithm into the LALR1 parsing table, we get the following table. The only difference is we get new shift values according to the new states we got in the previous one. For this, like if the transition is I0 to I36 for the C terminal, so for I0 we write S36 into terminal C. That's how you can see the changes. Now here also we see that there are no multiple entries in this table again, thus the grammar is LLR1 grammar. Okay, now let's consider another example and we'll clear the concepts focusing more on CLR1 and LLR1 tables. Let's consider another example. The given grammar is capital S gives capital A gives capital A, capital B, or epsilon, capital B gives small a, capital B slash small b. Now, what we do here is we check whether the grammar is unambiguous or not. So, as we see that there is no same left and right derivation from the same grammar, thus our grammar is unambiguous. Okay, so proceeding further, we calculate the first and follow for our given grammar. So for calculating the first and follow, we use the same for the algorithm as shown on the screen. So thus we calculate the follow for our given production as using the first rule we get follow of s is equal to dollar, as we did in the previous example, as same as over here also. Now taking the production capital A gives capital A, capital B, follow of A is equal to we get follow of A is equal to small a, small b, and dollar. Again we get follow of B is equal to small a, small b, dollar. Now we construct the augmented grammar for for constructing the CLR1 table. Thus we consider a new augmented grammar as capital S dash gives dot S. Now we will construct the canonical collection of LR1 items as we did in the previous example. Thus we use the following algorithm over here. Now since we have the grammar as S dash gives dot S comma dollar, S gives dot A comma dollar, A gives dot AB comma dollar, and S A gives dot A. For the first prediction we can see that the look ahead is dollar because after S dash we don't have any terminal. Okay, Thus, the look ahead is dollar. Now, since the uh, capital S, after the dot we have capital S, so we need to include all production starting from capital S. So we include capital S gives dot A into the I0 closure. Thus, the look ahead for S is also dollar because first of S is dollar. Okay. Now for the dot we have capital A. So we need to include all the production starting from capital A. Thus we have capital A gives dot AB dollar. Again we see that for the first of A we have the first of A is dollar. Again, so we see that look at A is dollar also. Now we include again another production as capital A gives dot. Here we see that after dot there is nothing, which means there is epsilon. Okay, thus the production is A gives dot. So we construct the similar uh, similarly we construct the whole canonical LR1 collection. Have a look at closely at this diagram. Okay, and analyze the canonical collection. We see that, yeah, we see that the canonical collection is the same as we did for the last example. Okay, so now moving on constructing the LALR1 parsing table. So for constructing the LALR1 parsing table, we use the following algorithm. This is the same algorithm which I showed you on the last example. Okay, so constructing the LALR1 parsing table. Constructing the LALR1 parsing table. Here also we write except according to second rule. If S dash gives S dot for dollar is in I of I, then action I of dollar is in except. So for the diagram, we see that for state I1 we have dollar S dash gives S dot comma dollar. Thus we include except in I1 row for dollar. Okay. Now writing shift and reduce similarly according to the algorithm and using this diagram for like the canonical LR1 collection diagram, we complete the whole table as like this. Okay, using the following algorithm. Moving on, we see that after the after the construction of LR1 parsing table, we see that there are no multiple entries into the same column. Okay, thus there is no conflict, hence it is a LR1 grammar. Okay, moving on, we construct the LR1 parsing table for the same. Thus our given grammar will be S gives capital A gives capital AB, capital A gives epsilon, capital B gives small a, capital B gives small b. Now we consider the augmented grammar as S dash gives S. Again, we construct the I0 canonical collection for this. Okay. Now again, what we see is an LALR1. We combine all the states with the same core into one state. Moving on to the LALR1 canonical collection, let's analyze closely. For states I4 and I7, we see that it has different cores. It has same cores but different look ahead values. As we can see that B gives A dot B, B gives A dot B, but the look ahead is dollar and A slash B. So again, we go to the LALR1 collection and we combine I4 7 states. Okay. Similarly, analyzing the other states also, we combine I6 and I9 to give I69, I5 and I8 to give I58. Again, the same I58 state over here also. Okay, this is how we construct the LALR1 collection. Okay, we use the same formula for we use the same algorithm as shown in the CLR1 canonical collection construction algorithm. Okay. Now moving on constructing the LALR1 parsing table. So after constructing this LALR1 parsing table, we use the same algorithm as shown in the previous CLR1 construction. So we construct the table as follows, and after constructing the table, we see that there are no multiple values, so there are no shift reduce or reduce conflicts. Thus, it is a LLR1 grammar. That's how we have learned constructing LL1, LR0, SLR1, CLR1, and LLR1 parsing tables. Now, next, our topic is activation trees. So, what does an activation tree mean? Let's consider a program. A program is a sequence of instructions combined into a number of procedures. Okay, so a program collectively is a sequence of instructions. Okay, which consist of number of procedures called together. Thus, in that program, instructions are executed sequentially into a procedure. Okay, so the execution of a procedure is called an activation. Now, for each procedure, we have an activation record for our program, whereas an activation record contains all the necessary information required to call a procedure. An activation record contains the following unit. First, temporaries. What temporaries does is it stores the temporary variables and the data required for a given procedure in a given program. Second, local data. Local data stores the data for a particular scope of a procedure. Next is machine status. Machine status stores the values of address codes and the jump codes into a separate address. Fourth is control link. It maintains the link of control between the different procedures. Fifth, access link. It defines the access of the program for different procedures. Sixth, actual parameters. Actual parameters are the parameters passed into the parenthesis and for a given procedure. Like if we call a function named as multiply bracket a comma b, thus a and b are the actual parameters passed into the function. Return value. Return value keeps the track of the return values given to the program. Next, let's consider a given example program as the one shown on your screen. The first statement is printf, enter your name. Second, scanf. Third, we call a procedure show data and pass an actual parameter username. Next is a printf statement, and then we have the definition of our procedure show data, in which we have a printf statement. So let's write the activation tree for the following program. Since we have the first printf statement and next scanf statement, so directly they are embedded into the activation tree as follows. Firstly, as the program begins, we have a printf statement record. Next, moving on, we have a scanf statement record. Next, since there was a procedure call of show data, we execute the show data procedure. So for that, we have a printf statement. We execute that, move back, and go to the tree. Then we execute the next printf statement, and then similarly finish the program towards the end and return the value to the program. Thus, how an activation tree is being processed. Next, what are the principal sources of optimization of a code? A compiler optimization must preserve the semantics of the original program. So while optimizing a given program, what the programmer need to keep in mind is the semantics of the original program are not lost while optimizing or transforming the code into one form to another. Okay, so the transformation can be of two types, global and local. Local transformation consists of looking within the basic block. So what while transforming, what we look is we look for code for optimization within the local scope, not in the global scope. The second one is global, looking across the block. So what while optimizing in the global scope, what we do is we look for the code which is redundant or not relevant outside the global scope of the block. Okay, that's how we optimize our code. Now functions that preserve transformation are including common subexpression elimination, copy propagation, dead code elimination, and constant fielding. Thus, what we need is now uh, for the first one, common subexpression elimination. What in this type of transformation, what we do is we exclude the common subexpressions. Like for a given program, if we have two printf statements printing the same statement, what we do is we remove the common statement and just keep a single copy of that. Okay, now second is copy propagation. In copy propagation, what we do is we pass the values from one procedure to another. Thus, the copy of a given data has been propagated from one part of the code to the another. This is known as copy propagation. Third is dead code elimination. Dead code elimination consists of a procedure where we exclude or delete a part of the code which is not relevant to our program. Like suppose we have many printf statements which are not relevant and are not useful for the program, but are increasing the space, execution time, and the type complexity. Thus we exclude these printf statements because they are dead code. So thus we eliminate the dead code and optimize the code itself. Now fourth part is constant fielding. In this thing, what we do is we include constant variables which increase the modularity of the program. Thus the code can be optimized further. Okay, thus these are the principal sources of optimization of a program. Finally, thank you for watching the video. Thank you.